Exponential growth and decay. Our objective for this video is we're going to look at some real-life applications in how you can model exponential growth and decay. Let's first off start by defining what this is. Exponential growth or decay is when a value increases growth or decreases decay at a rate directly proportional to, in other words, multiplied by a factor, its current value. Okay, growth means you have, exponential growth means you have a very fast increase. Exponential decay, you're getting very fast decreases. A growth example, you're doubling every time period. So you're multiplying by 2. A decay example, you're halving, which is multiplying by a half for each time period. Okay, so a couple of examples and just looking at the numbers and how this would work and some real life stuff. Let's talk about world population increasing at approximately 1.1% per year. What this means is that every year the world population is 1.1% more than it was the previous year. Okay, 1% more than the previous year means you multiply the beginning value of that year times 0.011. Okay, so we'll take a look at an example of that type of exponential growth. At the end of 2020, which we'll call year 0, the population of the world was about 7.6 billion. So the end of year 0, year 2020, we're at 7.6 billion. At the end of the first year, year 1, which would be the end of year 2021, you have 7.6 billion plus 1.1% times 7.6 billion, and now you're at 7.68 billion. That's the new starting number for year 2. And you multiply that number times 1.1% to get your new number, 7.77 billion. And then that's the starting number for year 3. You multiply that number times 1.1% to get 7.85 billion. And you can see it's increasing, and the increase will get faster and faster as you do this. That's exponential growth. Okay, compound money. Okay, compounding interest does the same thing. Okay, it's the same. The idea is that you earn interest on your interest. So here you have growth on your growth. Here you're going to have interest on your interest, have your money grow faster. For example, let's say deposit $10,000 and the account is paying 5%. As a decimal, that's 0.05 interest. And we're going to compound it 1 time per year. Start with 10,000. Year 1, you start with 10,000, you add on 5% of 10,000 and you have 10,500. Year 2, that's the new starting number. And then you get 5% of the new number, 11,025. Year 3, that's your new number. Then you get 5% of that new number, 11,576.25. And you can see the increases begin to get faster. This is a $25 increase. Whoops. This is a $26.25 increase. Okay, so it'll continue to get faster. It'll get faster and faster, and that we saw in a previous video how that might work. If you deposit money and let it sit there for like 33 years, this interest will grow faster and faster and faster. In banking, they call that interest on interest. And it's a very nice way to make money. So let's first take a look at how this looks. Give me a second here. Let's take a look at the model that's used and what it means. Okay, so here's our model for exponential growth and decay. We're going to use this formula right here. A is equal to A sub 0 times E, which is a natural number because This is what takes place in nature. We see this all around us, and that's where that letter E, the number E came from, raised to the K times T. What do these letters mean? Well, A sub 0 is the original amount, or the initial amount, or the size when you set time equal to 0. Okay, that's what you're starting with at whatever time you're calling 0. The A is the amount you have at time T. 30 years from now, you have this amount, or whatever. 20 years from now, you've got this amount. The K is a constant, okay? It represents the growth or the decay rate as a decimal. Now, we'll talk about the growth or decay rate as a percent, but using it here in this equation, we're going to write it as a decimal. If K is positive, we have a growth model. If our constant is positive, we have a growth model. If our constant is negative, we have a decay model. Okay? So the K there is our kicker, if you will. It's kind of the key piece of this. Here's how growth works. You have an initial size or an initial amount at time 0. So A sub 0 is that initial size or amount. In this case, K is positive, so you're going to get exponential growth over time T. So T is your independent variable, and A, the amount you're going to have, is your dependent variable. Decay, same idea. You have an initial amount at time 0, but in this case, our K, our constant, is negative, and so we're going to get decaying. And our final amount is going to be smaller and smaller and smaller exponentially. Okay, so what's the general idea behind this? Well, sometimes we're going to be given the initial amount or the size, A sub 0, and then amount A at a certain time. We're going to be told some information. We'll then have to use these data to come up with K. We got to come up with that constant. And then once we get K, we can go back and we can use this formula with any time we want to come up with a final amount. And that's the idea. We can use this equation down here, sorry about that, to make predictions. Let's do a couple of problems because that always helps. And I turn my paper over. And just a moment, let me get my paper set. I like to number my pages, and I hadn't done that. I left myself plenty of space to do these problems. Save yourself some space if you're writing this out by hand. Okay, example 1. The U.S. population in millions in 1970 was 203.3 million. By 2020, the population had grown to 331 million. Nice increase, almost a little over 100 million people in 50 years. Okay, find an exponential growth function. We're obviously growing. We're going from 203 to 331 that models the data for 1970 through 2020. That's letter A. Letter B, then we can use this function to predict what year when the population will reach 400 million. So letter A is basically find the constant K. We need to know the constant so we can make predictions. Okay, so letter A, we got to find the K. We know that our formula is A is equal to A sub 0 times E to the KT. What do we know? We know that in 1970, this would be our beginning amount, A sub 0. We know that our ending amount here, and let me push up my clipboard a little bit so I can write above that. This ending amount is A, okay? And I know that if I subtract these two, the time it took is 50 years. T is 50 years. And I know I have a growth function, so I know K is going to be positive. So I have a positive K. Well, let's find it. The ending amount is 331 million. Okay, the initial amount is 203.3 million. E is a number. I don't know K, but I know the time that it took to go from here to here was 50 years. Okay, so we can, let's first, we need to get at this exponent. Okay, so we've got to use some logarithms here to get at the exponent. But first, let's divide both sides by 203.3. So I'll divide this side by 203.3. That'll get rid of that. And I'll divide this side by 203.3. And I'm going to leave this right now. I'm not going to do any math with that. So now I have E to the 50K, I'm writing this just simply on the left side, is equal to 331 divided by 203.3. Okay, so here I am. And I need to get at, to find the exponent. I need to solve for that exponent. Well, I can use a log. Logs give me the exponent. Okay, this is a base E, so I'm going to use the natural log. So I'll take the natural log. Again, it's the base E, and that's the base. I'll put the E there just to show you, but you don't have to write it. Of 331 divided by 203.3, and that gives me the exponent. Okay, so here I use the inverse, which is the natural log. I rewrote it to get at the exponent because I need to figure out a way to get to this K. Now I can solve for K. Divide both sides by 50. And I get K is equal to the natural log of 331 divided by 203.3, all of that divided by 50, which equals 0.01. Okay, so what do I know? The exponential, what does the question say? Find the exponential growth function that models the data. Okay, the exponential, it's positive, so it's a growth function. K is positive. The exponential growth function that models the data from 1970 to 2020 is A equals the end result. The ending amount is 203.3 times E, and K is 0.01 to the 0.01 T. Okay, so we just found the model. We had to find K. Okay, we found K. We can now replace the K here, and now we can use our model to make predictions about the future. We know how we started, and now we can predict any time we want, and that's letter B. Use your function to predict which year the population will reach 400 million. Okay, so let's go down here. I've got my growth model, letter B. I know that A is equal to 203.3 times E to the 0.01 T, and I want to know, okay, what year am I going to hit 400 million? So let's put 400 million in for A, and let's solve for T. Okay, 203.3 times E to the 0.01 T. Well, I have an exponent, but I got to get rid of this 203.3 first so I can get at this with a natural log. I'll divide both sides by 203.3. And I'm going to leave it as a fraction and use my calculator only one time. So I know that E to the 0.01 T is equal to 400 divided by 203.3. And I'm back to here again. I need to get at this exponent. Need to find the exponent. I need to find a way to get to it to solve for t. I'm going to rewrite it in its logarithmic form. It's a base of e, so I'll say the natural log base e of 400 divided by 203.3 is equal to 0.01 times t. Okay, this is the inverse, which in this case again was the natural log. Remember, the log outputs the exponent. I need to get to this exponent, so I'm going to rewrite it in the log form so I can get at it. Okay, so t is equal to this big old thing, natural log of 400 divided by 203.3. All of that divided by 0.01. That can go into a calculator, and that comes out to approximately 68. And we go back up to here, and we note that t, let's see here, time. Oh yeah, so t is the number of years since 1970, okay? It doesn't say that as clearly as it should, but we know that t is the number of years since 1970. So this is number of years. Doesn't really say that at all, I don't think. Number of years, because year 0 is 1970. So this is the number of years since 1970. Okay, so the population will reach, according to this model, the population will reach 400 million, that's a lot of people, in the year 2038, which of course is 1970 plus 68. Remember, 1970 was our year 0. So we need to add 68 to that 1970 to find out when we're going to reach 400 million. All right, let's do one more example. Let's do one that involves decay and how scientists use carbon-14 to date old stuff. Okay, here we are. I'm gonna get myself straight, sorry about that. So carbon-14 is a radioactive isotope. I'm not a chemist, but that's obviously some type of a chemical or something. And it's used to determine the ages of old things like fossils and artifacts, because carbon-14 decays at a constant rate. Okay, we know the decay rate of carbon-14, and we can make use of that to find the ages of things. So, example 2. After 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. So this is a fact, and this fact can help us find the model. We want to A, find the model, the decay model for carbon-14, and then B, we want to use that model to help us answer this question. In 1947, the Dead Sea Scrolls were found. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. We'll use our model to estimate the age of the Dead Sea Scrolls at the time they were found in 1947. Okay, so we first got to find K. So this is our find our decay rate. And as we know, it's a decay, so K should be less than 0. All right, so letter A, we know I have A is equal to A sub 0 times E to the KT. Okay, after 5,715 years. That's T. A given amount of carbon-14 is now half the amount. So the original amount is down to half. So we'll take the original amount is still A sub 0. I don't know what it is, but the ending amount is 1/2 of A sub 0. The original amount, after 5,715 years, we have half of the original amount. Half of is 1/2 multiplied. E times K, and we know that, let's see if I can't write my K better than that. We know that our time is 5,715 years. So now we can find K. First thing, we have an A sub 0 on both sides, so I can cancel those out. That's a common factor. And I know I'll put this on the left. So E to the 5,715 times K is equal to 1/2. And I'm back where I was previously. I have an exponential function. I need to get to the exponent. I need to find the exponent. I need to solve for the exponent. I have exponential equation, so I'll rewrite it using its inverse, which is the log, and I'll use the natural log because my base is E. So I have the natural log of 1/2, base E, is equal to 5,715 times K. So the inverse, which is the natural log, allowed me to get it out of the exponent and get it someplace where I can do some algebra on it. So let's divide both sides by 5,715. And our constant, it should be negative, is the natural log of 1/2 divided by 5,715. And it comes out to be approximately negative. Good thing, because it's a decay. Got a lot of zeros, a lot being 3. And we're going to go all the way out to 6 places for this one. Okay, so that's our constant for this situation. It tells us our model. Again, look at letter A up here. Find the exponential decay model. So what's our model? Our model is A is equal to A, oops, not A sub 0. Sure, it's A sub 0 times E to the K, so negative 0.000121 times T. Okay, now let's do part B. Part B says, go back up here, sorry about that. Part B says, use your model, okay? What they found had 76% of the original. Well, the original is A sub 0, so 76% of it means that A is 0.76 times A sub 0. Okay, so let's get our decay model out here. We know our model is A, the final amount, is equal to the original amount times E raised to the negative 0.000, 121 T. Okay, what they found had 76%, so 0.76% of the original. That means 76% is 0.76 times the original, and that equals the original times E to the negative 0.000121 times T. Now we're just going to solve for T. Well, those are common to both, so we can cancel those out. And we wind up with E to the negative 0.000121 times T equals 0.76. And by now you know the drill. We've got an exponential. We have an unknown in our exponent. We need to get at it, so we're going to use the log to do that because the log will give us the exponent. This has a base of E, so we can use the natural log, okay? And so we're going to use the natural log the natural log of 0.76 is equal to our exponent, which is a negative 0.00121 times t. And now we can divide both sides by negative 0.000121. So t is equal to the natural log of 0.76 divided by negative 0.000121. And this comes out to be, I'll put curly equal signs, approximately equal to 2,268 years old when found in 1947 at the, oops, almost got you there. There we go. I have this piece. I put this into a calculator. I get the answer of 22,268 years old when found in 1947. So there you have it, some word problems with growth and decay, very popular. Exponential growth with populations and exponential decay with figuring out how to date old stuff. Makes use of both exponential and logarithms.